Hi, good morning, everyone. Today we will start our lecture. Still we are in the initial value problem, and in the initial value problem today we will learn the third technique, which is basically, as we will see, is actually extension of the previous ones, which is the Runge Kutta method. Runge and Kutta, they are two Germans who developed this method, and hence the name of the method comes of their names, combination of their two names. Okay, so this is the most popular method that we use to solve a differential equation, and it's a fourth order method. When we say fourth order, we expect that there is first order, second order, etc. Without going into details, I will not go into the proof or the mathematical proof, but we want to see how we'll apply the method. Okay, so the Euler method, the first method, it's actually nothing but the first order Runge Kutta method, and the Euler modified version is the second order, and so on and so forth. Now, the order that we talked about here is how many terms of the Taylor series derivative are included. And as we know that, the more we include, the higher the accuracy of our approximation. So when we say a fourth order, means we have 4 derivatives, including the first term, which is, so this will make it 5 terms. However, the whole idea here that we want to approximate it without using any derivatives. So without going into any mathematical proof for the Runge Kutta, let's just see the method. Assume that this is the same, we put it in the same format as we used in the Euler method and the modified Euler method. So we put the function in that format. If dy by dx in one side, remember this is still first order differential equation, and the rest we'll put it in the other side, and we will have one initial condition. Now, the solution of the Runge Kutta method is summarized as such, that the value of y at the existing is equal to yn and 4 different values, k1 to k4, and if you count the number of terms is 1, here 2k2, so we make it 3, 2k3, so 5, and then k4, so it's 6. This is why we divide by 6 here. We're taking the average of these, or a weighted average, maybe this is a correct term, weighted average of these 4 terms. But what are those 4 terms? The 4 terms are defined as follows. So k1 is equal to h f x of n y of n, which, if you remember clearly, this is the Euler method, okay? And this is the term we also start with. We call it the predictor in the modified Euler method, okay? Then we have k2. Now k2 it's a function of 2 terms. This is the x term, and this is the y term. Now, the x term is xn, the initial value, plus half the increment, h. On the other hand, the y is yn plus half k1, which is, you take it from the previous step. Now, k3, same thing for the x of n, and yn now it depends on k2, so you take it from the previous step. Finally, k4 is h, xn plus h, yn, and k3 was also take it from the previous step. So as you can see here, each step depends on the previous step. So without going into a mathematical proof, there is a mathematical proof for this, but that's not in the scope of the course. I mean, numerical method, there are 2 different ways of teaching it or studying it. The mathematicians and the engineers. When it comes to the mathematicians, they are very much interested to the proof of the formulas, to the convergence of the formula, and they go into deep details in how to prove the method and how to try to show the convergence of that. We as engineers, we are more interested into the applications. Uh, Sometimes you have seen during the course, I give you some proofs or some convergence, but this is just to have the taste of it. It's not really the focus of the course. The focus of the course should be how I can apply this method to my engineering problems. And this is always the case between us, engineers, and scientists. Scientists, they develop the theory, develop the method, either physicists, chemists, or mathematicians, and we engineers, we come and take their theory and try to apply it. And I always say a joke here in this regard. When you see in terms of how much you know and how much you are gaining as a salary, there is an interesting relationship here. So you probably know that the most intellect scientists are the physicists, the chemists, and the mathematicians, and those are the ones who will always win the Nobel Prize. Okay, but unfortunately, they are the least paid in every aspect. In all, always scientists are the least paid. Now, we engineers, on the other hand, we are a bit less intellect than scientists, but we take their effort, their work, and we change it into applications, and we are much more paid than them. And then there are the business people who may not have any intellect at all and took our ideas and applications and change that into a commercial product, and they get most of the money. So you can say that your intellectual ability and your income are inversely proportional. The more intellect you are, expect less salary. Okay, this is a joke. I love to repeat it every time. Okay, so let's have a look here into this example. So this is exactly the same example we did in the Euler method and the modified Euler method. So here we have dy by dx equal to 2xy. We have the initial condition. This is my x0 and this is my y0. And we want to use the fourth order Runge Kutta method to approximate y 1.5 using h as equal to 0.5, and we know the actual answer from the previous discussion. So this is the formula we remind ourselves. So we need to find K1, K2, K3, and K4. And what I will do with you now, trying to see how we can find these terms. So we have h is equal to 0.1. This is the step. So we start with K1, with, as I said, it's nothing but the Euler method. So here, h times f of x of n, y of n, okay, which is equal to h is 0.1, and this will be your f of x0, y0, the function defined at x0, y0, and we know that this is nothing but 2 x of 0, y0, because this is the function, okay? And we know x of 0 and y of 0, so from this you can say easily that K1 is 0.1 times 2 times 1 times 1, and this is equal to 0.2. So this is your K1. Now your K2, now here it is, we have to be careful when we do the substitution. K2 is nothing but equal to h, the function defined at x of n plus half of h. And so this is the x point of the function, and the y is yn plus 1/2 K1. So this is equal to 0.1, which is the h, times the function at x of 0 plus 1/2 times 0.1, comma, y0 plus 1/2 times 0.2. Okay, now as I said, we know x of 0 and we know y of 0. So this K2 now will be equal to 0.1. Now the function is equal to 2x of 0, y 0, so it becomes 2 times, this is your x of 0, which is x0 plus 1/2 0.1 times the y0, which is y0 plus 1/2 times 0.2. Now, we know what is x of 0, which is 1, and we know y of 0 is also 1. So now we have everything, 0.1 times 2 times 1 plus 1/2 equal to 0.1, so it is 1.05. And this 1 plus 1.1. So if you do the calculation, you will find this is equal to 0.231. So we found K2. Now let's find K3. Now once you understand how we implement this, now this becomes trivial. Now comes like it's a sort of a repetition. So here we have h times f of x of n plus 1/2 h. So it's exactly the same thing as in the previous. Now the only difference here is the y-axis, which is yn plus 1/2 K2. Everything is the same. The only difference between K2 and K3 that the y-axis, the last term is equal to K2. So now when we substitute, we have everything. We know h, we already have it. X of n, we know it. Y n in h. So the only thing I have to substitute here, and instead of 0.21, I will put this value, which is 0.231. And if I do the calculations, this is equal to 0.234. And you can go on 3 maybe. Depends how many digits you wanna go. Okay. Now we'll go for K4. K4 is equal to h times x of n plus h, comma, yn plus K3. So we know x, so this is equal to h2 of x0 plus h times y0 plus K3. This is the function. Okay, so we know everything. We know y0, x0, h, K3. If we do the substitution, this becomes 0.27153. Okay, now we are set to come and substitute the value of yn. Okay, now y1 will equal to y0, the initial condition, plus 1/6 K1 plus 2K2 plus 2K3 plus K4. Now we have everything, and this is equal to 1.2337. And if we see the full solution here now, and when you move to reach to 1.5, this is the approximation, 3.4902, and the true answer is 3.4904. So it's correct to the 1, 2, 3, 4 digits. Okay, so the error is almost 0 here. Okay, so this is, if you recall, we have like around 16% when we use error method, around 2 to 3% when we use the modified, but this now almost we are reaching to 0. So this is really a very good method, and when you search the methods for solving a differential equation, this is the standard method. This is the most popular and used method, the Runge Kutta number degree 4. Okay. Now I always like to link this course to real life. I don't like to have this course only just numerical methods. Yes, you can solve. Now this is differential equations. No, okay, for us as electrical and computer engineers, we have seen differential equations when we dealt with circuit. We dealt with first order differential equation when we dealt with one component, one inductor or one capacitor, and you used in circuit the step-by-step method. I don't think you used the differential equation approach to solve the circuit, but now also I think you are now studying second order circuit. Maybe you have already studied that and used the Laplace to solve higher order differential equations. typically second order differential equation. When you have two elements, two storage elements like an inductor and a capacitor, then you have to deal with a second order differential equation. In tomorrow's lecture, we'll talk about how we can solve a second order differential equation. But today I'd like to go through this example and see how I can convert this typical circuit problem that you have done it before and use the differential, first the differential equation approach to write the equations instead of using the step-by-step method and using a ready formula. And then we'll see how we will use the Euler methods, the modified Euler method, and the Runge Kutta method to solve them and compare the accuracy for all of them. Now, this circuit, as you can see, we have here a voltage source, DC to DC sources. And we want to find in the following circuit, find the current that goes through the inductor. So I want to find this current I. Now, as we know, the inductor is a storage element, so it is either will be either charging or discharging. So we are interested to see how the current will behave when the switch is changing from one position to another. So basically, the circuit was the switch was at that position. At t equal to 0, this switch is open, and we want to find at this configuration what will be the current at t equal to 0.1 until we reach 0.5 seconds, and we will use 0.1 step or h equal to 0.1. Okay, so we want to see what is the current at 0.1, 0.2, 0.3, 0.4, etc. Okay, now we will hear the question says Euler and modified Euler method. I will also show you the answer for the Runge Kutta method as well. Okay, we will show you only the final answer, and you can easily derive that. Now, as we know that we need to have first differential equation and also the initial conditions. None is given to us here. We don't have the differential equation, nor we have the initial conditions. So we need to find the initial conditions. Now, to find the initial conditions, we need to solve the circuit at t less than 0. So the switch, we assume that the switch stays for this position for a very long time, meaning that if you have an inductor, will be fully charged. If we have a capacitor, will be fully charged as well. The inductor will be a short circuit. The capacitor will be an open circuit. So if this is the case, this switch was going this way, okay? And basically, this is I1, I2, and I3, and the inductor is converted to a short circuit because it was fully charged. Okay, very good. Now, let's find I3, which will be our initial condition. We need that. We need a differential equations in terms of I3, and we need also the initial condition. What was the current value before we moved the switch? So we'll solve this circuit to find I3. So we'll use nodal analysis, KCL at V0. So assuming the currents are leaving the node, so it becomes V0 minus 12 divided by 2 plus V0 minus 4 divided by 2 plus V0 divided by 2 equal to 0. And to solve for this, you will find your V0 is equal to 8/3 volt. Okay, now I want to find I3. I3 is nothing but V0 divided by 2. My I3 equal to V0 divided by 2, which is equal to 4/3 amps, and this is my initial condition. This is my initial condition. This is how we find the initial conditions in real problems. Usually you are not given the initial condition. You have to find the initial conditions. And in our case, most of the time this is applied to circuits. So the initial conditions for us is the current in the inductor, because as we know, the inductor stores the energy as a magnetic field, so it is in the form of a current, and or the voltage in a capacitor. This is the initial condition, because we know that the capacitor stores the energy as an electric field or in the form of voltage. So now I0. Okay, now we will move from t less than 0 to the moment we close the switch. So t just equal to 0, and we want to see what is going on. So this is the circuit now. So this becomes an open circuit, and we will have one big loop, only just one loop. This is floating in the circuit, so this is not really contributing to anything now. Okay, and now we expect that the current in the inductor will not change instantaneously, because the inductor is a device that holds the magnetic field. The magnetic field cannot change instantaneously, and hence the current cannot change instantaneously. Now we'll see how the circuit will look like, or as such. So now I need to take a KVL to apply KVL. Now when you apply KVL, you will have 2I plus what is the voltage across the inductor. We know that the voltage in the inductor is L di by dt. So this becomes 2 di by dt plus another 2I minus 12 equal to 0. Now, as we agreed that we have to put the formula in this format, dy by dx equal to f of x and y. dy by dx this is the derivative term, and this is the derivative of the dependent variable with respect to the independent variable. So here this is dy by dt. So 2 di by dt, I will keep it in one side. This is equal to 12 minus 4I divided by 2 both sides. So your di by dt is equal to 6 minus 2I. And this is my equation. Now I start working with numerical now. Now this is the moment, and I will start working in numerical method. Before, I am an electrical engineer who is analyzing a circuit, a system of equations that I'm dealing with, and I want to put it into the form that is suitable to apply the numerical method, which is the tool that I am using. Okay, but please do not forget that you are an electrical or a computer engineer. Okay, the numerical method for you and for us is a tool, only a tool to help us solve an electrical or a computer engineering problem. This is the reason why I'm bringing these examples, to just remind ourselves that this numerical method is a tool for us, and the bigger picture is that we are dealing with electrical and computer systems, and those systems need to be solved, and the numerical method is a tool that helps us to do that. Okay, excellent. So my function, the function in terms of the t and I is equal to 6 minus 2I. Okay, excellent. Now I need to find the current. So now we'll start with the Euler methods. We know that I n plus 1, so the current at the existing time step, because now we are using time as our steps, is equal to I of the previous time step plus h times f of t n I n, because these are the two variables I will have. Okay, so the current, now I know the current at I of 0, which is our initial conditions. We know that. Now, so my in, so this is equal to in plus h times 6 minus 2in. Okay, so excellent. So now I need to find, I know I of 0, we already know it. We already found is equal to 4 over 6. So I know I of 0. Now I need I of 0.1. I of 0.1 is equal to I of 0 plus h, which is 0.1 times 6 minus 2I of 0. So this is the formula that we will be using. Okay. Now this is, remember again, I n plus 1 is equal to I n plus h f x of n y of n. Okay. Now I of 0 is 4 over 3 plus 0.1, 6 minus 2I of 0 minus 2, 4 over 3. And this gives me 1.667. Depends how many digits you want. Okay. Now we know the exact solution of this. I of t is equal to 3 minus 5 over 3 e to the minus of t divided by 0.5. This is the actual or the exact answer of this. Okay. Now, if you use the step-by-step method, you will use this. If you solve the differential equation using any closed form approach, then you will get this. So we know the exact answer for this one. Now, if we compare the exact from the relative error, okay, so this is the approximate value, okay. So this is the at t equal to 0, which is 4 over 3, 1.33. At 0.1 is 1.667. Okay, and so on and so forth. Okay, and the this is the exact values. Of course, the exact values are matching at t equal to 0 because this was the initial condition. I'm not really doing any. This is a real value. I'm not doing any approximation yet. Then we see here the error, and here the error goes from 1.909 to 2.807%, which is reasonable. Now. Someone may ask, but in a previous example, the error was like 16% when we use the Euler method. Yes, it depends on the nature of the equation. Sometimes the nature of the equation does not deviate too much from the Euler method, and sometimes it does. It depends on how abrupt is the change in the function as we proceed with the dependent variable, which is in this case is the time. Here is something interesting here that you should notice. Now, as t goes to infinity, this will change back to another short circuit, will be fully charged. Okay, so the current I will become equal to 12. So I at infinity is equal to 12 divided by 2 plus 2. 2 plus 2, so this is equal to 3 amps. So it was 4 over 3, and then go to 3 over 3 amps, and this is clearly in the formula. As t goes to infinity, this becomes 0, so it's equal to 3 amps. Okay, so the current was the inductor was charged to 4 over 3, but that was not the maximum charge it can hold, because once I change the configuration, I will have, now here we have 2 voltage sources opposing to each other. Now I will have another voltage, that this 12 becomes alone, then this will give me even more charge to the inductor. Okay, excellent. So this is how we approach. This is how we approach the Euler method. Just before we proceed for the modified, let's see the question here. The question: how do you know what xn is? Xn is the initial condition. Okay, so remember we have that the initial condition here is equal to it was at 0. This is the initial condition, and here in this specific question, this is the time the switch changes position at t equal to 0. So this is my initial condition. So the time at which the initial condition happened, this is your x of n, okay, which is 0 in this case, and the value at that specific instance is your yn. Okay. Now let's use the modified Euler method. In the modified Euler method, we will have the corrector, the predictor, and the corrector. Now we know that now the predictor is x star n plus 1, which is equal to in plus h, the function at defined at t NIN, we know that this is nothing but the Euler method. So your I star at point 1, this is equal to 1.667. I don't need to solve this because this is exactly from the previous step. Now I need to find the corrector, which is I1, which is equal to I0 plus H, okay, times 6 minus 2 I of n plus 6 minus 2 I of n star divided by 2. Now we have here, this becomes I0 and this is I0 actually. Okay, so we have two values. The I0, that is the value of the current, which is we just found, and the corrector value. So this is 4/3, and this is 1.667, and H is 0.1, and this is the initial conditions, which is 4/3. So we have everything here. So if we substitute, this becomes equal to 1.633 amps. And here is the full answer for us here. So the full answer now for I is, you can see here the error has dropped from 2% to 0.2%, which is really very, very good value, very good approximation. Now you can also use the Runge Kutta. Now, as you can expect, the Runge Kutta, it would be like much more demanding. So I will just give you the value here. You can go and check that yourself. So your I at 0.1, no, this is using the Runge Kutta, equal to 1.6354, which is with, if you try it with this one, the error becomes almost equal to 0. Okay. So with this, we end up our lecture about the Runge Kutta. Now what is left is two concepts. I will see if I can finish them tomorrow. Or I think maybe we can finish them tomorrow. We'll have higher order differential equation, and it's not very difficult. You know how, we'll see how we will deal with them. It is basically, we will change a second order differential equation into two first order differential equations, and then we will use the Euler method or modified Euler method or Runge Kutta to solve both of them. So it's just repetition what we have done, but it's the approach of the problem. Then the second topic will be how to deal with, all these are called initial value problems. So we need to know the initial value of the inductor, the initial value of the capacitor. There is another set of problems called the boundary value problems. Okay, here we need to, it's more like a space. We need to find the boundaries, or could be the time as well. I need to know the boundary between two limits, and then I want to find in between that this limit. But more, it is more or less used in space, and we'll talk about that more maybe tomorrow or maximum by Thursday.